Welcome to week 1 of Electricity and Magnetism for Educators. This week is a little bit of a test. Since there's so many of you with such a broad range of backgrounds, I really need to get your feedback on this week's video. I need you to tell me if I'm going too fast, if I'm going too slow, if you want me to include more detail or less detail. So make sure you give me that feedback in the problem solving discussion. I'll adjust next week's video accordingly. And if you want me to go over some of the stuff that I'm going to talk about today in more detail next week, please do let me know. Okay, so what we're going to talk about today is we're going to start talking about divergence, curl, and vector fields. So in the review videos, I did include a video called Divergence, Curl, and Vector Fields. So we're going to build on that. Some of it is going to be review, some of it we're going to expand upon. So I just want to start off by talking about why we care about divergence, curl, and vector fields. They are extremely important to understanding electricity and magnetism. And though I talked about that in my other video, I really want to make sure I want to talk about it in the video for this course because it's so important. So bear with me if you've heard this before. The reason we care so much about divergence and curl and vector fields is because we can't read Maxwell's equations without them. So let's remind ourselves what Maxwell's equations are. Please bear with me as I adjust to writing in my tablet again. It's been a couple months. All right. Okay, so E, as you may have guessed, stands for the electric field, and B stands for the magnetic field. These are both vector fields. You can think of a vector field as what you would see, like if you're looking at a map of the United States and you see a map of what the wind is everywhere, you have little arrows representing the wind everywhere. You know, something like this. So you have vectors at every point representing wind speed. We do the same thing with electric and magnetic fields. We have an arrow to represent the electric field or the magnetic field at each point in space. That's what a vector field is. So Maxwell's equations, so you see the symbol here, little grad symbol. So that, with a little dot, means divergence. Now you would never see del dot written by itself. It would always be next to a vector function. And here we see the del cross, that's curl. So we're going to need to talk about what divergence and curl are in order to read these equations. Other things you need to know about are partial derivatives, so that's what this del dt is. Now, a partial derivative is nothing fancy. It works just like a regular derivative, but when you have a function of multiple variables, say you have a function of x and y, and say you want to take the derivative where x is the variable and you treat y as a constant, then you write del dx. If, say, you want to treat x as a constant as y as the variable, then you say del dy. So here we have the time derivative of the magnetic field. So the magnetic field is a function of time, and of the spatial coordinates, x, y, and z, or depending on your coordinate system. So this says that we only care about the time derivative of the magnetic field. This says that we only care about the time derivative of the electric field. So what these equations tell us is that the divergence of the electric field is determined by this here. The divergence of the magnetic field has to be zero. The curl of the electric field is determined by the time derivative of the magnetic field. The curl of the magnetic field is determined by a current and the time derivative of the electric field. That's a whole lot of information, and if you don't know what divergence and curl mean and you're not accustomed to looking at vector fields, that's not going to make a whole lot of sense yet. So let's go ahead and look at what divergence and curl mean. We'll come back to looking at Maxwell's equations many times. So if what I just told you about what they mean doesn't make sense yet, just take notes of the words I used and know that we're going to come back to talking about all of them. Okay, so let's talk about what divergence means conceptually. Divergence is a measure of how much a vector field is spreading out. So let's say you had a vector field that looks like this. So the vector field tells you that everything's spreading out from the center. That's going to have positive divergence. Or say you have a field where the arrows are pointing in. That's kind of a sink. That's going to have a negative divergence because everything's getting pushed together. And curl is what it sounds like. If you want to use another word, you could say it's a swirl. Think of curl like if you have a whirlpool. It often helps to think of these things in terms of water. Like here you have a source of water, and here you have a sink of water, and here's a whirlpool. So vector fields can have curl and divergence at the same time. So Maxwell's equations tell us how to figure out the divergence and curl of the fields that we care about. So what one of Maxwell's equations tell us is that electric charges are a source of divergence of electric fields. And they tell us that a current carrying wire is a source of curl in a magnetic field. Okay, so that gives us some conceptual idea of what's going on. Let's work on practicing our calculations. So, how do we calculate divergence? Today, I'm only going to get into detail on how to calculate divergence because I want to get your feedback on the right level of detail before I do any more. If you're bored and you want me to go faster, if you're overwhelmed and you want me to slow down, if it's just right, just tell me anyway. I need to know. Okay, so the way you calculate divergence. So you take the x component of your vector field and you take the partial derivative with respect to x. You take the y component of your vector field, you take the y derivative. You take the z component, you take the z derivative. So what are the components? Well, alright. Physics teachers normally know a lot about vectors, but I'm guessing you use the magnitude and direction notation most of the time. I'm not sure about the AP curriculum. Let me know what notation you use for vectors in your classes. In my intro class, I do introduce this type of notation, and this is what we're going to use most of the time. You might also write these as I hat, J hat, K hat, and that's my preferred notation. I'm just more used to it. So you put the X component next to X hat, the Y component next to Y hat, the Z component next to Z hat. Let me know if you understand this notation. If a lot of you tell me that you don't know what this means, I'll make sure to cover that more next week. Okay, let's look at an example. I, for one, never think these things make a lot of sense until I see an example. So we'll be doing two different types of examples today. We'll do some where mathematically doing the calculations is easy and it lets us draw the picture and really understand what's going on. But I'm also going to give you some that are more of a pain to calculate, just to get you warmed up for what we'll be doing this year. But those are going to be harder to understand conceptually because they don't necessarily translate into nice pictures. So to start with, yes, my coordinate system came out very crooked. As I said, it's been a little while since I've used the tablet. So we have a function that's a vector field that's x cubed x hat. X hat tells you it only has an x component, so it can only point in the x direction, either positive or negative. And it's x cubed, so when x is 1, it's just 1. When x is 2, it's 8. So this is a function where the arrows get longer and longer the farther away from the x-axis you go. And they're the same length no matter what y is. Okay, but cubed is an odd function, so that means that it is negative on the other side. Okay, and when you're sketching these things, don't worry about being exact. Just draw enough arrows that you understand the general behavior of the function. Alright, so what's the x component of this function? X cubed. And there's no y hat or z hat, so the y and z components are 0. Okay, so we go to calculate our divergence. Okay, so we're taking the derivative of x cubed with respect to x. Well, it's only a function of x, so that's not too bad. So we get 3x squared. That's just a simple power rule. Let's look at what that means. So that means that the divergence is always positive. Does this always look like it's spreading out? Yeah, it does. And it says that the divergence is bigger the further away from x equals 0 you get. Does it look like it's spreading out more the further away from x equals 0 you get? Yes, it does. So that one seems to make sense. Now we're going to do an example where I'm going to force you to practice your calculus, but it's not going to make any sense to draw really. Well, it will be a pain in the neck to draw, so we're not going to worry about that. So as you can imagine, drawing this will be pretty hard to figure out. So we're not going to do that. I've written this as a mess just for you to exercise your basic calculus muscles. So let's calculate our divergence. So we'll need to take the derivative with respect to x of the x component, the derivative with respect to y of the y component, and the derivative with respect to z of the z component. Alright, what do we get? So we're only taking the derivative with respect to x. That means y is a constant. It might as well be the number 4 for all we care. So that y is going to be left alone. The derivative of sine x is cosine x. You're going to want to make sure that you know the derivatives for your trig functions because we're going to use them all the time. Alright, this next one, the derivative with respect to y. Okay, this is e to the y. That's an easy one. That's just e to the y. Exponential special. Okay, now for this next one, the derivative with respect to z. 4y cubed is not a function of z. Y might as well be a constant. So that's 0. Alright, then we need to take the derivative of minus 1 over z cubed. The way I like to do that, and if you are one of the people who's been teaching calculus, or you're teaching APC, you probably are pretty good at this already, is that I rewrite it as e to the minus 3. That makes taking the derivative easier. Okay, so you bring down the minus 3, multiply that times the minus sign, so you end up with plus 3, and then you have z knock down the power, minus 4. Alright, that's our divergence. So the way I normally do these videos is I'll do a few examples and then I'll give you some to try yourself. That way you make sure you're up to speed before you go any further into the video. So I'm going to give you 3 functions and I want you to calculate the divergence of each one. This one's not too bad to draw, so I recommend you sketch it to make sure your answer makes sense. I do not recommend drawing this one. This one you could draw. Okay, so pause the video, work these out. If you have any problems with them, please just go ahead and go to the problem solving discussion or email me or type questions in my virtual office. I will get to you. Or maybe one of your classmates can help you. But once you're done trying it out, go ahead and press play and continue watching the video. Alright, let's calculate the divergence for this first one. So we're taking the derivative with respect to x of x squared and the derivative with respect to y of y squared. That gives us 2x plus 2y. Let's look at the picture to make sure this makes sense. Again, it's just a rough sketch, nothing perfect. Well, if it's just on the x-axis, it points in the x direction, and it gets bigger as you get further away. And it's always pointing in the positive direction. When you're in the first quadrant, you'll get something like this. When it's just on the y-axis, you'll get something like this. X squared and y squared are always positive, so your vector always needs to point in the positive x and y direction. But it's going to be bigger the further away from the origin you get. And this says it has positive divergence in this quadrant. It says it has negative divergence in this quadrant. So it's getting pushed together here, spreading out over here, and over here, and over here, whether it has positive or negative divergence. Depends on whether x or y is bigger. So this one is a little bit tricky to think about, but you can get some idea of what's going on. Okay, this one we are not going to draw. Okay, so we're taking the derivative of u to the z cosine x with respect to x. Well, e to the z is just a constant. The derivative of cosine x is minus sine x. We're taking the derivative of sine 2y with respect to y, so this requires using the chain rule. So a 2 comes out. Derivative of sine is cosine. Then we take the derivative of minus xy with respect to z. That's just 0. Okay, done. So the tricky business with this one is just remembering one of these functions is a constant. The trick here is you have to use the chain rule. And this is remembering that x and y is a constant. Okay, last one. Alright, the derivative of minus x with respect to x is minus 1. The derivative of minus y with respect to y, minus 1. This is always minus 2. So look at a picture. This function looks like this. Everything's pointing inward, so it has negative divergence. That makes sense. So we can do this. We can see that makes sense graphically. And this reviews what I talked about in my video, my math methods class that I shared with you. Now I have talked about this a little bit differently than I did in the other video. The way I did in my previous video was I focused more on looking at divergence as a dot product. This is an equally valid way of looking at it, and I just like to give you multiple perspectives. But we've been using rectangular coordinates for all of this, x, y, z. A lot of situations we look at in electricity and magnetism, those coordinates aren't the best coordinates, and I'll give you a couple examples why. Okay, so let's say we're talking about the electric field of a point charge. You have your point charge. The electric field's pointing out from it in all directions. Excuse my terrible drawing. This is for a positive point charge, like a proton. So really the best way to describe that, you'd say this has spherical symmetry because you have arrows going out in every direction. So you'd rather use spherical coordinates. Or let's say you have a current carrying wire. Well, the magnetic field that goes around this wire goes around like this. So in this case, this is a situation that has cylindrical symmetry. So it would make more sense to use cylindrical coordinates. So I just want to spend a few minutes talking about spherical and cylindrical coordinates. So if you spent much time teaching math classes, or you were a physics major, this may sound familiar. Cylindrical coordinates are a lot like polar coordinates, if you're familiar with those. Okay, so let's look at those coordinate systems. My drawings look nice on my paper. Here's hoping I can make them look nice on these slides. Okay, so in Cartesian coordinates, you just define a point by its position x, y, z. In spherical coordinates, you define it by the length of this vector here between the origin and your point. You define it by the angle with the x-axis, which we call phi, and the angle with the z-axis we call theta. If you are a math major, you may think this sounds backwards. This is because physicists and mathematicians reverse which angle they call theta and which one they call phi. But we're in physics class right now, so this is what we're doing. I would probably get it backwards all the time if I tried to use a math convention. So if you're familiar with unit vectors, you know that x hat, y hat, and z hat always point in the same direction. But when we're talking about the vectors r hat, theta hat, and phi hat, the directions of these vectors changes depending on where your point is here, because r hat always extends out this way. Theta hat extends this way. Phi hat extends this way. And so, say if you were at a point over here, then phi hat goes this way instead. I'm trying to draw 3D. Not sure if it's working for you. Let me know if this is hard for you to visualize. And I will try to find a 3D picture online. I bet there are good resources out there for making pictures. So if you know your x and your r and your theta and your phi and you want to convert between them, here's the conversion. This is just a bit of geometry, or trig, I suppose. Okay, so x, y, and z all span from minus infinity to positive infinity, but these do not. R goes from 0 to infinity, theta goes from 0 to pi, and phi goes from 0 to 2 pi. And we'll get to this in a little bit, but in part because r hat, theta hat, and phi hat are changing directions, it actually turns out that calculating divergence in spherical coordinates is kind of a mess. If you want to know the full why behind that, your book has a decent explanation of it, but if you just want to know how to do it, we're going to cover that in this video. When it comes down to math, I'll skim over the derivations because I really want to get to the physics. Okay, now let's look at the cylindrical coordinate system. I think my last drawing came out pretty well. Hopefully you agree. Okay, now we're in cylindrical coordinates. So in cylindrical, your point is defined by the length of this line segment here, which we'll call S, the length of this segment here, which we call Z. Z is still Z. You are actually only changing x and y to s and phi, and this angle phi. So this is really a 3D version of polar coordinates. In polar coordinates, you normally use r instead of s, but we don't want to get ourselves mixed up with spherical coordinates. Okay, so now our unit vectors are s hat, phi hat, and z hat. Z hat always points in the same direction, but S hat points out this way, phi hat points around this way. So as your point changes, those vectors do change direction. And that's something you're going to have to keep in mind as we get into more problems later. Now if you want to convert between Cartesian coordinates, so rectangular coordinates, and cylindrical coordinates, this is how you do it. So S runs from 0 to infinity, phi runs from 0 to 2 pi, Z is unchanged and goes from negative infinity to positive infinity. Okay, so that's your brief rundown of other coordinate systems. You can do a little geometry and some trig to make sense of this on your own. Let me know if you want me to talk about it more. Now I want to talk about the ramifications for calculating divergence. So as I said, your unit vectors are changing direction. It does funny things to your divergence. So here's some messy expressions to remember. Well, I don't expect you to memorize any of this. This class is definitely not about memorizing. Alright, so if you're in spherical coordinates, and you need to calculate divergence. This is how you do it. Okay, see, kind of a mess. So you're still, you see, taking the derivative with respect to r of the r component, and the derivative with respect to theta, the theta component, and the derivative with respect to phi of the phi component, but there's all this extra stuff in here. Again, if you want to know why, I recommend reading your book. I don't want to spend our class time delving into that. Now, if you have cylindrical coordinates, it's a mess, but it's not quite as bad. See, we still have extra stuff in here. So we have the derivative with respect to s, there's the s component. We have the derivative with respect to phi, there's the phi component. We have the derivative with respect to z, there's the z component. Notice the z part is unchanged because the unit vector is unchanged. But the s component and the phi component still have a little bit of extra stuff going on. Okay, so let's do an example. I'm going to start with an example where the arithmetic is not too bad and it's reasonable to make sense of it. Okay, so we're in spherical coordinates, see, because we have r and r hat. There's no theta or phi components, so these are just 0. The theta and phi parts are just going to give us 0. So then we just have to deal with our component. So in this one, the divergence is 1 over r squared. Let's look at our picture. Oh, that line is not straight. Okay, so this is a function that's always in the positive r hat direction. That means it's always pointing away from the origin. And it's 1 over r, so that means it gets smaller as you get further away from the origin. Does that make sense with the divergence? So we have 1 over r squared. So the divergence is always positive. Yes, it's spreading out, but it's spreading out less as you get further away from the origin. Yes, that makes sense. Okay, now let's do an example that makes you practice some of your calculus more, and we definitely do not want to draw. We'll do this one in cylindrical coordinates. Okay, so we need to take the derivative of this with respect to s. That requires the product rule. So say we take the derivative of s, leave e to the minus s alone, we get e to the minus s. Then we take the derivative of e to the minus s and leave s alone. So it gives us minus s e to the minus s. Okay, next one, our 1 over s out front, the derivative of cosine phi with respect to phi is minus sine phi. And s may as well be a constant as far as e is concerned, so that's 0. We can clean it up a little bit. Well, I'm not sure this is cleaning it up that much. Okay, so I made you practice your calculus. Now I'm going to give you a few to practice yourself so you can practice finding divergence in cylindrical and spherical coordinates. You can tell whether you're in cylindrical and spherical coordinates by whether you have s's, phi's, and z's, or r's, thetas, and phi's. This one you could draw if you wanted to. This one I'm making a mess so that you practice your calculus. Normally I prefer to avoid making a mess, but since this is the beginning of the semester, I want to make sure that you practice your calculus. Especially because when you're taking partial derivatives, it's easy to get confused about what's the constant and what's the variable. Alright, so pause the video and work these out. Again, I encourage you to discuss these in the problem solving discussion. Alright, press play again when you're ready to go. Okay, this first one is not too bad. So we just have the theta hat and phi hat components are 0. Okay, that's supposed to be a 4, but my tablet appears to have connected it, so it looks more like a 9. This is a 4. Okay, so we have a negative divergence. Because r to the fourth is always positive, this is always a negative divergence. The divergence gets smaller as you move further away from the origin. That makes sense for this function. Alright, this next one is a mess. You're really going to have to exercise your calculus muscles. Which I suppose is your brain. I wanted to avoid writing more, So I skipped a step here and went ahead and multiplied the r squared through here. I multiplied the sine theta through here. Let me know if that bothers you. Remember, the sine phi is just a constant. Well, one's a constant, so that's 0. Here, cosine theta is a constant. And we just take the derivative of sine phi, get cosine phi. This doesn't clean up that well. You're welcome to rearrange to your heart's content. That's really a matter of personal preference, how much you want to clean things up. I mean, you definitely want to get rid of the 0. And you could make this sine theta or cosine theta, so you can make it tangent theta on the bottom, but it's up to you, really. Alright, last one is some practice with cylindrical coordinates. Okay, so cosine phi is a constant. Now minus s squared is a constant. The derivative of cosine phi is minus sine phi. So there I'm going to flip the sign. The derivative of z with respect to z is just 1. I'll clean this up a little bit. Okay, so these really messy ones don't really look like real physical situations. I just made them messy so you would practice your calculus more. The ones you can draw pictures of are really the ones I prefer. I really want to spend more time on concepts. I just want to get you warmed up on your arithmetic. So your feedback's really valuable to me. Also, you are required to participate in the problem solving discussions, and part of the reason is just because I need your feedback. I always need your feedback. It's really important to me. If you want to read more about any of this, it's in chapter 1 of your textbook, and also you can go back and look at the other review videos as needed. I was gonna get into calculating curl and line integrals today, but I decided that I really want to get more of your feedback first. Alright, well, I look forward to hearing from you, and I'll see you later.